here we should start our actually the first class of teaching by taking a look at the lecture notes set number 1. So as you can see, it is a very long set of lecture notes, 130 pages. I'm sure that if you are attending this class, you probably have learned more than 70% of the materials inside this set of lecture notes. And so my way of handling this set of notes is I would just go through some of the important titles. So there are some concepts that are fundamental to the study of the physics 1, and they are somehow it is somehow necessary for me to even briefly mention them to make sure that everybody is aligned to the course. So I will just mention the title, or maybe explain briefly the concepts. In the more important cases, I would be going through 1 or 2 examples. And if any of you have particular questions, you could always ask me, for example, during the break. And of course, since I have obtained some of your requests and from the wish list, I would go through those topics in the wish list a little bit more in details. So as you will see in this set of notes, the main idea is concerned with the linear mechanics. How we are approaching this topic? Well, I mean, in the teaching of the physics 1, we have 2 major topics in mechanics: the linear mechanics and the rotational mechanics. The traditional way of handling the linear mechanics, at least, is it is much like how the people study the science handle the topics. Of course, at the beginning, they don't know what has happened. They have observations. So they see what is happening in the universe or in their daily lives. In order to understand what is happening, the first thing, of course, is they try to describe it to their neighbors. Well, say you have a classmate right next to you and you told him that, yeah, yesterday I saw a car running into the wall. It doesn't crash the car. How strange. So it is the verbal description. But from time to time, having isolated instances, isolated accidents, for example, does not seem to make any good use to the society. Of course, I'm not saying car crashing is very useful for the society, but if you could understand what makes the car crash and what prevents the car from crashing, that is very important. So in order to make good use of them, they start to describe, not just by words, but by mathematics, what is happening. And that comes to the topic of kinematics. So if you have the lecture notes with you, you will see in chapter 2, there is the topic of motion in 1 dimension. They are firstly describing what is happening. And so it comes to the equations that you are quite familiar with. I will go into them a little bit later. The acceleration, the relation between displacement, velocity, and acceleration. So in particular, we will be focusing on constant acceleration motion. Constant acceleration motion. How does the object behave? How does the object move when it has a constant acceleration? First, they describe what is happening by means of equations, mathematics. Later, Isaac Newton, as you probably know, one day he was sitting under the apple tree and then the apple hits on his head, and all of a sudden he has discovered the universal gravitation. Okay, that's not a related story, but he is the guy who has got the next step to move forward the linear mechanics and asking the important question, why? Not just focusing on how the object moves, but then the next question is why the object moves. And so he has come up with the concept of force. And that is why we have the 3 Newton's laws. So you see the logic. At the beginning, we describe, and then we try to understand why. So in the next set, well, the next set is actually projectile motion, which is still related to the kinematic. I'll understand why. And then in the lecture notes, in the unit number 5, and that starts from page 37. Page 37. Then it starts with the laws of motion. Here we start to describe why. And that comes to the concept of the force, which is central to the understanding of the mechanics. And in the unit number 6, we would have the circular motion. So unit number 6, we have the circular motion. That is a special kind of linear motion. The thing is, you could treat it as a linear motion, but with constantly changing velocity. The direction changes, although the speed does not change. So that is the major idea, how we are approaching the linear mechanics. And of course, when the techniques get more advanced, we need some more tools. Apart from using the concept of force, we have some other useful parameters or quantities that we can describe the universe. And that is the energy, as well as the linear momentum. So it is because when we only have the force to describe the behavior of objects, sometimes it is not quite efficient. In many cases, we may not even know what is the force between them, but there are other parameters which we could characterize, which we could measure the behavior of the objects, and that would be energy as well as linear momentum. Those are some other tools, if you like, that we can use to assess the behavior of the objects when they are undergoing linear motion. So that is the main idea of the whole topic of linear mechanics. And as I said, I would be going through most of them quite quickly, and from time to time I will work on some sample questions in your lecture notes, maybe 1 or 2 tutorial questions later next week, and that would be the whole agenda. If you have any questions, you could ask me during the break or in the consultation hours, which happens tomorrow morning. So we first have to start from the very basic, which as I said, I will go through them very quickly. These are the topics we have learned: displacement, velocity, and acceleration. Note that we are not using scalar quantities, we are using vector quantities. I hope you know what it is meant by the scalar and vector quantities. Scalar and vectors. Scalar quantities are the quantities which has only the dimension, the magnitude. How big is that? How long is that? How far away is that? It tells you the size, but it does not tell you the direction. If you have a quantity that has both a magnitude as well as a direction, then they are what we call the vector quantities. As written at here, displacement, velocity, and accelerations, they are vectors. They are vector quantities. Now, if you have studied physics in the high school, you may have to do a little bit of a translation, and I probably have to put up some reference materials for you to do the translation, maybe next lecture. But if you have gone through the lecture notes, you probably would have guessed what it is meant by displacement, velocity, and acceleration. So if I go to the next page, sorry. Okay. So here, this is just a very quick introduction on how to describe the motion. Of course, when you are doing it in a high school, you no longer use them anymore. So I will skip it very quickly. Okay. And there are quantities which are vectors and scalars. As I just mentioned, vectors are the ones that require the specification of both the direction and their magnitude. By contrast, scalars have just the magnitude. Directions may not make much sense for them. For example, the distance and the speed, they are the scalar quantities. If you want to fully describe them, you need to use if you want to fully describe the motion of objects, you need to use vector quantities, for example. And SI units, presumably you have learned about them, so I will not once again go into the details at here. If you are interested in the definition of various SI units, you could always go to this link to see the definition of various SI units. And in the physics or in many of the science subjects, we frequently use a prefix in order to simplify our units. The prefix are summarized at here. The more typical ones that you have used may be the small letter m, small letter c, say in the millimeter or centimeter, or small letter k, as in the case of the kilograms. Although, please remember that kg is by itself the standard SI unit. Standard SI unit is kg, not g. G instead is the derived one, which is 1,000th of a kilogram. There are other prefixes that you would be used more often from now on. For example, mega, giga, and tera. These ones, I presume you are more familiar with these days when you talk about the size of the files. Megabytes are, well, in the old days, very powerful, but these days they are really nothing. Gigabytes are more typical, especially for the movies, and terabytes describe the hard disk. 1 or 2 terabytes are the typical size of the hard disk. So the notation as well as the corresponding power are written at here. So I'm not once again going into the details. Now, we have just talked about the displacement, velocity, as well as acceleration. And of course, they are related to one another. So the relation among them is the time. The idea of the velocity is described here. It is the what we call rate of change of displacement with respect to time. So here we have a very important concept in physics called the rate. The rate is always the change of quantity over the change of time. So I don't have the symbol writing through here, so I just write dt. The change of the quantity over the change of time. This is always the case. When we talk about the rate, we are always talking about the change of a quantity over a certain unit of time. So here you can see that the velocity, for example, is the change of displacement from a certain location over a certain period of time, delta s over delta t. Similarly, acceleration is delta v over delta t, change of the velocity as over a certain period of time. So, for example, from the left to the right, we can see the displacement from a certain point over a function of time. If it is a linear change of the displacement with respect to time, you could always determine the velocity by measuring how much change, delta s, over a certain period of time, delta t. Well, I hope you understand it is a straight line. So this is the meaning of the velocity, which basically representing the slope of this line, And similarly, acceleration is delta v over delta t. If it is a flat line, it has zero slope and it has zero acceleration. Now, all these are very good because the change is gradual. The change is linear. But what if you have a change that is not gradual? For example, in the next page, you have this. Now, over the linear parts of this displacement versus time graph, you could see that the changes are gradual. So you could easily draw, for example, the VT graph, something like that. So this is a certain slope. 10 over 2 is 5, so 5. At the very beginning, and it is a constant slope. And then from the second to the 4th second, it has reduced to half. And remember, the change is negative, so it has a negative velocity, minus 2.5, something like that. Now, here, from here to here, you have a sudden change of the velocity. So, what is the corresponding acceleration? Now, if you just focus on the first 2 seconds, acceleration is 0. There is no acceleration. But then, if you talk about changing the velocity from 5 to minus 2.5 over basically a time of 0 seconds, then you would say that the acceleration curve would look something like this. At the first 2 seconds, it may be, I use another color, it may be 0. And then over the next 2 seconds, it is also 0. But then right in between, you have a very sharp change. So what happens at here? There is a very great acceleration if you are considering over a short period of time. But if you are considering, say, over a time of 4 seconds in total, then the acceleration value would be quite different. It may not be exactly the same as you consider time right within the region around 2 seconds. And this comes to a very important concept of instantaneous values. Versus average value. For the average value, it is just a change over a certain duration of the time. So if you draw it like that, maybe I would turn on actually the camera up here. So if you are talking about a curve something like this, this is, for example, S, and this is, for example, T. Then, if you're talking about in between these 2 points, there is a corresponding change of time, delta T, and there is a corresponding delta S. The average value, average velocity, would be delta S over delta T. But it does not stop you from making delta T very small. What I mean is you are starting to move this point closer and closer to this location. So when delta T tends to 0, you would have what we call the instantaneous velocity or instantaneous value in general. The instantaneous velocity would be how we write it as a limit where delta T goes to 0 for the average value. And this would be actually the concept of differentiation. So in the physics, in many situations, we would be looking at not the average value, but the instantaneous value, because the instantaneous value would determine some important physical properties. As we would explain, for example, in the case of the circular motion. If you go around a circle, the average velocity is 0. Because you finish one circle, you come back to the same point. But the instantaneous velocity changes whenever you move around the circle. So there would be a continuous change in velocity, and therefore there must be an acceleration. If you use the concept of an average acceleration, you will fail to solve anything in the circular motion. And in many of the physics problems, you will see the values, the instantaneous values. And that would be, let me see. Go back to the lecture notes first. That would be shown in small characters. The instantaneous values are usually shown in small characters, where if you have the average values, typically they would be written with the letters AVG at the back. But at the beginning, we try to make it very clear to you whether it is an instantaneous value or the average values. Typically, without mentioning, they would be corresponding to the instantaneous values. Okay. So I just like to highlight the difference between the average values and the instantaneous values in the previous descriptions. Now, as I mentioned, once we have got the equations, once we have got the parameters of the displacement, velocity, and acceleration, the next thing we would like to do is to describe the behavior of the objects, especially in the case when they are under constant or uniform acceleration. And these are the equations which I believe you have learned before. So let's try to see if I'm showing myself clearly. Okay, I'm still on it. Okay, so here you have the equations that describe the motion of the objects when they are under uniform or constant accelerations. The deviation of these parameters, they could be obtained. They could be obtained move forward. Okay. Yeah, they could have been obtained by considering, for example, this graph. The first equation is a very general one. When you have a constant acceleration, that means the velocity is changing linearly with respect to time. So this is the general equation, and the equation for this form is always written in this way: final value minus initial value. On the top, it is the velocity. So final velocity minus initial velocity. The time at the bottom is the same. Final time minus initial time. So this would be the equation, and you would obtain the first kinematics equation. The second one is concerned with the relation between the velocity and the displacement. So the change of the displacement, the delta S is equal to the average velocity divided by 2 multiplied by the time, because if the velocity changes linearly, it is changing by the same amount over a fixed period of time. So the average velocity can be obtained by just adding the final and the initial velocities and divided by 2. And then you would have it multiplied by time to give you the average displacement. And by combining these two equations, we could obtain the more complicated pairs of equations, which connects the displacement with the time, acceleration, and the initial velocity. Or if you do not have the time, you may connect the final and initial velocities to the acceleration as well as the displacement. So, well, I mean, yes, you are expected to know how they are derived, but this is a constantly coming up question. Many of the students think that physics is like history, in the sense that they have to memorize anything. My suggestion is don't. Please don't do that. I will show you a very good example a little bit later. The equations in physics are not for memorizing. They are there for you to understand. First, you have to understand them. And then we can actually work them out more easily. So question 3 is VT instead of V2. Okay, maybe, yeah, some typing mistakes. The ones in the last page should be the more appropriate ones. Okay, I have to find a way to move up and down. yeah, the equations in this page should be the more appropriate one. I hope, yeah, this would be the ones that are correct. These should be the correct version. Yeah, I would try to revise the equations later, so to update you the correct equations. But here, these ones should be correct in this page, if that is agreeable to you. Why is F1 plus V, well, why is VF plus VI divided by 2? It is just the case when you are having a constant acceleration and you will have the velocity that keeps changing from time to time. So this is the changing velocity. So you could always find out the average velocity because the velocity is changing linearly with respect to time. So you could find out the average velocity, which is happening right in the middle, because that is a linearly changing property. And when you multiply that average velocity to the overall time, you would get the displacement, or as some of the classmates explained, that could be understood as the area under the trapezium. So that is these are the two ways which you could understand. And actually, when you talk about the area under the trapezium, that comes naturally to the concept of integration as well. So if you are finding out the velocity from the displacement versus time graph, or if you are finding out the acceleration from the velocity versus the time graph, you could do the opposite. You could find out what is the changing velocity as a function of time by finding out the area under the acceleration versus time graph as the time changes. As you are increasing the area, for example, as you are increasing the area through the increase of time, this corresponds actually to an increasing velocity, as you can see. So the value of the velocity is actually corresponding to the increasing area. So that is why you could interchangeably calculate the acceleration and the velocity. When you want the acceleration from velocity, you do differentiation. When you want velocity from acceleration, you do integration, finding out the area under the graph. That is the basic idea. Of course, if some of the classmates have done integration before, they know that I'm missing something. They know that I'm missing the constant term. Because when you are adding up the area, it does not tell you what is the initial value. It can be starting from 6 or 9 and so on. But the rate of change is the same. So in any case, we are not trying to focus at this point. We are trying to actually having a summary on these 4 equations. And yes, thanks to the classmates who point out the problem of the equations in this page, I would try to figure it. I will try to revise it. I believe it is only the equation number 3 that has the mistake. If you have found other equations that have mistake, please help me to please point it out to me. Okay. And with that set of equations, we are ready to do some business of calculation. And some of the important types of questions involve, for example, the calculating of the motion of a freely falling objects. We could do that because whenever the object is falling freely, it is under the acceleration by the gravitational field. So it is under the Earth's gravity's influence, and it has a uniform value basically on the surface of the Earth around 9.8 meter per second square. Or that is the typical value, I would say. This is just a typical value on the surface of the Earth. When you move a little bit further away, this value changes. And also, if you go deep into the ground, going closer to the center of the Earth, this will change as well. But on the surface of the Earth, this is around 9.8 meter per square second. And whenever you use it, it should be very distinguishable from other parameters such as gram, but it should be quite obvious when it comes to the question. Okay, so as I said, the deviation of the equations, yes, I would expect you to understand how they are derived, but of course, you would have very limited memory capacity. Well, I would not say that because many of the students can memorize all the nationals, but at the end, you will forget things very quickly. So my understanding is you try to get hold of some important concepts. And once you know those concepts, you could always work out the steps in between. And in any case, we would provide you with a standard set of equations during the examination. So those are the starting points for your calculations. All the other stuff, you could choose to memorize them, but the physics problems are never the same in every single question. We will see a little bit later. When you change a parameter a little bit, things will change quite a lot. And you may not be able to use the equation at all. So we would be showing those examples a little bit later. So here you have the example of calculating the motion of an object under free fall. You have the guy that is throwing a ball vertically upward, and then it falls vertically downward to the ground. And the equations that you use are basically the four equations we have just seen. For example, in the case here, we consider t equals to 0 at the point where the object leaves the man at the top of the building. And we try to determine the time that it takes when it reaches the maximum height. So we have to understand what is happening. At the beginning, the ball has to acquire a certain velocity in order to go upward. If it does not have a certain velocity, it would just go straight downward instead of going upward. So when the ball leaves the man's hand, it must have a certain upward velocity. And this velocity would keep on decreasing because of the acceleration due to gravity that points downwards. So sign of symbols are important. The signs of the acceleration and the signs of the velocity, they are very important. If you want to find out the time that the ball reaches the maximum location, you have to use the equation at here, final velocity minus initial velocity divided by time equals to acceleration. So y here corresponds to the y direction. So the vertical direction is considered as a y direction. Upward values are taken as positive, downward values are taken as negative. So final velocity, it is the velocity at top of flight, 0. And then the instantaneous velocity moving up by 20 meters per second. So that is 20. Acceleration points downward, minus 9.8 meters per square second. So in this way, you calculate the time accordingly. Maximum height can be obtained once you have got the time by using this equation. So this, as I've said, is something I would expect you to have learned before. So I'm not going into deep details, and you could try to go through the steps one by one in order to understand the problem. And here, I would instead go through a little bit about the concept of the vectors, because that is one of the topics in the wish list. So a very brief review on the vector quantity is that it is something that is described both by a number and a direction. So two vectors are the same only when they have the same size as well as the same direction. If the direction changes, the two vectors are not the same. On the other hand, if they are just displaced by a certain amount, but they have the same direction and same length, then the vectors are identical. So when we are drawing the vectors, as in a diagram, the length of the arrows would correspond to the size or the magnitude of the vector, and the direction should be the one that corresponds to the direction of the vector quantity. Here it tells you the situation where you have the scalar measurement of the distance moving from A to B. You could have many different paths to move from A to B, but at the end, the vector of displacement from A to B, there is only one, and that is the straight arrow pointing from A towards B. So that is the difference between the two. And the vector notations in the physics, there are several different, in the physics questions, there are several different ways to write down the vector. You could either use a letter and cap it with an arrow, so to indicate that it has a direction, so that is a vector. Or sometimes in the textbook or in the questions, they simply bold the letter. These letters are not bold, they are not thicker in size. This one is bold, it is thicker in size. So these are the vector notations. These are how we write down the vectors. And of course, vectors have both the magnitude as well as direction. If we want to specify, we are just talking about the size of the vector, we could use different ways. For example, instead of writing the bold letter, we use the simple letter, or maybe put it into italic. This would indicate it is a size of the vector without mentioning the direction. Or we put two vertical lines to sandwich the vector notation. And in this way, we also would understand it as just the size of the vector without considering the direction. Here you have a number of vectors, and in terms of physics, they would be considered as identical. As I've said, as long as two vectors have the same size and they are pointing in the same direction, you could displace them freely in the space, and they would be able to match with one another. because they have the same size and same direction. And so they would be considered as eco-vectors. And there are some interesting ways in which we operate with the vectors. For example, when we are adding up the vectors, we do it in this way. We try to put the arrows head to tail or tip to tail. So if you are having an A vector that is lying horizontally and a B vector lying in a certain angle, if you consider the addition of these two vectors, you put the tip of one vector to the tail of the other vector. So in this way, it is A vector plus B vector. It is A vector plus B vector. Alternatively, you could also say, I am not adding it in this pattern. I am adding it in the way of B vector plus A vector. In this way, it would first be going along the B vector, and then you move along the A vector. Notice that here, I have moved the A vector from this point to this point. At the end, you will see if you are adding B vector to A vector, it will be this one. The vectors A plus B would be identical to the vector B plus A. So these and these, they are having the same length and pointing in the same direction. So they would be identical. Adding the two vectors can be done in a reversible order. You could reverse the order of addition. And there is another important point to note about the vectors, and that is the negative vector. The negative vectors are important because that would lead to the subtraction of vectors naturally. A negative vector is basically one that has equal size but opposite direction with the original vector. So here, if you have a B vector, the negative B vector is the one that has the same size but points in opposite direction to the original B vector. So this would come up to the case of subtraction of vectors. If you want to have, say, A minus B, A vector minus B vector, it would be, first, you try to draw a minus B vector like this, and then you add A vector to minus B vector. So A plus minus B, and that would be the C vector if you like. Similarly, of course, you could have minus B vector plus A vector. Minus B vector, if you draw it, it would be something like that. Minus B vector plus A vector, it would be this vector. This is the final one. And this final vector would be identical to this C vector, which is A minus B. So that is how we consider the minus vectors or the negative vectors. Subtracting vectors is just the addition of a negative vector, if you like. So that is how we consider the subtraction of vectors and negative vectors. And in the vector notations, sometimes it's also useful to consider what we call components of the vectors. By the components, we are saying that the vectors could actually be considered as a sum of two other vectors, or a sum of a multiple number of vectors. Usually, we try to make it simple. We try to separate them into 2 or 3 vectors that are what we call independent of one another. It is kind of like you are trying to separate the components into what we call the X, Y graph paper, or if you are 3-dimensional, it will be X, Y, and then the Z direction coordinate space. So if you use the concept of the coordinates, things would become much easier. So we cannot see the Z at here, but we could see the Z at here. Any vectors could be what we call resolved into the components. Resolve into components. The components are the vectors along the X and Y and Z direction. When you add these X, Y, Z components together in the vector form, you would get back the original vector. So how does it work? Say at here, you have the A vector, and you put it on the X, Y coordinate system. Try to make good use of the X, Y coordinate system. Put that tail of the vector at the origin. So in this way, it is very easy. You just try to find the X component by, well, trigonometric function, A cosine theta. And the Y component, A sine theta. So in this way, you have the X and Y components. And in order to make it easy to understand that they are vectors, we could rewrite the A vector into something like this. A vector is AX times I vector. This I vector has a property that it has a length of 1, and it points along the x-axis direction. And then plus AYJ vector. J vector is having the property that it points in the y direction and has a length of 1. So these are what we call unit vectors. These are what we call the unit vectors. Unit vectors. And they are perpendicular to one another, so they would not be interfering with one another in the calculation. So in this way, calculation of vectors becomes quite easy, because whenever we have the addition of vectors, you just group the I vectors together and the J vectors together, kind of like you are moving along the graph paper. If you are having an A vector points like that and B vector points like that, you are individually making the motion along the x-axis by AX plus BX, and the motion along y-axis AY plus BY. At the end, this would be the final value of the vector A plus B. So these should be quite straightforward to understand, and as long as you make good use of the coordinate system, that should be quite easy to figure out how the vector is operating. So is there any questions about the vectors and kinematic equations? If not, I would take a break about 5 minutes at here, and then afterwards we would be moving to the case of the projectile motion as well as the Newton's law. Okay, so at the moment I would also be addressing questions from you all. Well, I mean, okay, IJK vector is just the extension from 2D to 3D. And the operation is under the same concept. They are perpendicular to one another, so adding up I, j, k vectors should not interfere with one another. So it's easy to add the third dimension into the calculation. If you go back to here, you have the ijk. ijk, yes, especially in 362, because we would be handling motion in the xy plane, and then some other properties would come up in the z plane. Remember left-hand rule. Okay, I would need to take a break just to get a little bit of rest. So I will come back a little bit later. Okay, so let us try to carry on with a very short break. Now we would be still under the topic of kinematics, but uh, uh, apart from the situation of object free falling in a one-dimensional way, like in the example of a man throwing a ball vertically upward, it is not very interesting. It is not very useful in terms of physics. More often, you will see the objects moving in a two-dimensional, at least, or most of the time, three-dimensional situation. And that is what comes next, the motion in the two dimensions. Now, in a certain sense, whether it is two-dimension or three-dimension depends on how you position yourself. You could always move the plane to contain the projectile motion, and then it will become a two-dimensional motion. So whether it's two-dimensional or three-dimension is really a matter of point of view. So here it is a topic that discusses the motion of the projectiles as a special application of the two-dimensional kinematic equations. The name sounds scary, but actually it is just the same, exactly the same set of equations. Or we could make it even more simpler by considering as a motion in two different directions. The impact is that we may have to consider different situations for the two directions. So where do you see two-dimensional motions or the projectile motion? Of course, you have done that before. Say, you may have played, I guess, the Angry Bird. So this is how the projectile motion would take place. Or for the teenagers, they would play different kinds of ball games, volleyball, basketball, football, then, or even you throw the stone for different reasons. And this would come up with a projectile motion. The importance of the projectile motion is that you would have definitely a constant acceleration, but this constant acceleration, because it is a vector, it has a certain direction. The direction of this constant acceleration is always downwards. Remember, when you throw an object, there would be acceleration due to gravity. And considering in the very practical sense, the surface is flat. You are not throwing a rocket, you are just throwing a piece of stone. So it is good enough to consider the earth is flat right under your feet. So the acceleration is just a vertical one. And then in the horizontal direction, on the other hand, there would be no acceleration because you are not accelerating the object in the horizontal direction. We must say that we are neglecting any frictional force. So in the projectile motion, we are considering the motion to be two independent motions. We are considering the projectile motion to be one which consists of two independent motions, which are associated with the x and y axis. And very importantly, any influence in the y direction does not affect the motion in the x direction. So this is very important because from that we could start treating the two-dimensional motion as two problems, two separate problems. So let us take a look how it works. For example, at here you have an object. Let me delete all the things. You have an object that is being thrown at A, and it would undergo a projectile motion because when it is thrown, it has a certain velocity. This velocity makes an angle theta I with the horizontal direction. So you would fully expect the object to be moving upward, and then gradually it would not go up anymore and start to come back again. And at the same time, the object would be moving forward as well. Finally, if you throw the object from the ground level, then it would reach again to the ground level some distance away from you, which is the range. And it would just hit on the ground. So you would be seeing this type of a behavior. Next question is, how do we analyze the behavior? As we mentioned, we try to analyze one problem like this into two separate problems. The first problem is the motion along the x direction. The second problem is the motion along the y direction. So that is what we do in the next page. Motion in the two directions are independent. So we could consider them separately, but the total time for the two motions are exactly the same. That means the object, when it flies from A to E, in the two directions, they take exactly the same time, because in the end, it is just one single motion. So we consider at here first the y direction motion. The y velocity, initially it is vi sine theta, upward motion. And then finally, if you are considering the y direction motion from A to C, that means to the highest point. Finally, when it reaches C, which is the highest point, it should stop rising anymore. Yf equals to 0. Acceleration in the y direction, it is -g because that is being pulled by gravity. And the displacement is the maximum height reached by the projectile motion. So Sy is equal to h. You could then use the one-dimensional kinematic equations. For example, at here, we use Vf squared minus Vi squared equals to 2a delta S. So in this way, we calculate the displacement in the S direction, and this would help us to determine the maximum height reachable by the object. And similarly, we could calculate the time required for the object to reach the maximum height. So that is quite straightforward if you use the one-dimensional kinematic equation and consider only the y-axis motion. Next step, we try to consider the range. Now, to consider the range, we need to consider the x-direction motion. This x-direction motion is not under any acceleration. It is not under any acceleration. So the velocity is constant along an x-axis. Vxi is equal to Vi cosine theta I. And actually, at any point throughout the projectile motion, the horizontal velocity is the same. Acceleration along x, 0. Maximum displacement, the range is r. So distance from A to E is r. question is, how do we determine what is this one? Now, here, it has written very simply that TE is equal to 2 times TC. You could actually determine it by further deviation, that the time from A to C is actually equal to the time taken from C to A. They have the same displacement, from vertical displacement from A to C, and from C to E, they have the same vertical displacement, same downward acceleration. So the time to move from A to C should be the same as the time to move from C to E. So that is actually logical to make this statement. And here it is stated quite plainly without any explanation. But in any case, we could make use of this fact, and we put it into the equation as equals to Vt plus 1/2 AT squared. And actually, I don't think you would need to use the 1/2 AT squared at all, because you just need to put in Vxi, which is Vi cosine theta I, and multiply by the total time, Te, 2Vi sine theta I over G. So in this way, you would calculate what is the range. Now, students would always be curious to know, as you have just demonstrated in the question and answer session. Okay. Why is TC equals to this one? You can find it at here in the previous page. Okay. So students would always ask the same question: do I need to memorize equations? Yes. If you remember the equations, as I've said, you have more than enough to memorize them in a history lesson. So at here, we have written down the two equations and even put it into the red boxes for the vertical height and the range. Why we are putting them in the red boxes? It is because we want to highlight their relation with velocity and the angle. We are not trying to ask you to memorize it because that is put in the red box and looks important. Well, okay, they are important because we want to show you the physics, but they are not important because we want you to memorize them. First, let's take a look at the equation for h, sine square theta I over 2g. What would be the condition for reaching a maximum height? If you have the same velocity, same initial velocity, in order to reach the greatest height, in order to maximize the h, you would put theta equals to 90 degrees, which is basically throwing the stone upward directly, vertically. But if you do that, theta equals to 90 degrees, then when you put it into the range, you will see, and even if you don't use the equation, you would immediately understand that the stone would hit back to you. It would not move any distance away from you. So, in order to maximize the range, on the other hand, you need to maximize sine 2 theta, because Vi and G, we assume them to be constant. Sine 2 theta is maximum when 2 theta is equal to 90 degrees, or 4 theta equals to 45 degrees. So that is when you throw the stone at an angle of 45 degrees, you'll reach a maximum range. Now, again, this is under the condition that firstly, velocity is constant, which is easy. And secondly, you are throwing the stone on a level ground. You are throwing the stone on a level ground, meaning that you start from h equals to 0 and end up at h equals to 0 as well. And then the two equations are valid. I could promise you things are never that simple, as you will see. And here, let us take a look at a simple example first. Now, you are trying to throw a piece of stone at an angle of 30 degrees upward into the air from the top of a building. How long does it take to reach the ground? Now, once again, you are having this two-dimensional problem. Try to separate them into two individual problems, one along the x direction, one along the y direction. So, how long does it take for the stone to reach the ground? It is the y direction problem. Because along the y direction, you have the acceleration downwards due to gravity. So we would solve for the y direction. Yf equals to yi plus, well, that is delta y equals to vyit plus 1/2 ayt squared. The final position is 45 meters under the feet. The initial position is taken as 0, so that is why minus 45 as the final initial 0. Vi, you're throwing it upward, so it is 10 meters per second, because initially it is 20 meters per second as a vector. So the vertical component is 10 meters per second. It has a downward acceleration due to gravity, so minus 9.8 meters per square second. So in this way, you calculate the time t. I try to address that question a little bit later, cosine 30 degrees, but I mean, at least the concept goes like this. So here, the next one is the speed of the stone before it strikes the ground. Now, for the speed, we are talking about the magnitude of the final velocity, So the idea is, I try to figure out if it is the case. 30 degree cosine theta multiplied by 20, 17.32. So I have the calculator calculating 20 times cosine 30 degrees equals to 17.32. So 17.3 seems reasonable. In any way, so firstly, we find out what is the velocity in different directions. Along the y direction, when it hits on the ground, it has a velocity of minus 31.3 meters per second, because the time is calculated 4.22 seconds. And the x velocity, it is constant, vi cosine 20. So by Pythagoras theorem, or by vector addition, if you like, it is the y component velocity squared plus x component velocity squared. Well, let me see. Here, yeah, the x component velocity squared, y component velocity squared. and then add them together, take the square root, it would be the final velocity magnitude or the speed of the particle when it hits the ground. So, okay, 17.3 is not exact, but of course, in your final exam calculations, you would leave maybe 3 or 4 decimal points more than the required in the answer, and then you carry those numbers into your calculation. Now, we try to take a look at this example. So, in this example, you are asked to find out the distance where the skier lands. So, you may calculate, of course, x or y, but here the locations are different in terms of the height. So you cannot directly use the range equation, but instead you have the similar problem actually in the previous example that I discussed. So it is always good to consider the motion in 2 directions and then consider them as separate problems to solve. So in the beginning, you have the x direction motion, x equals to vx times t, y equals to, of course, one-dimensional kinematic equation for constant acceleration. And the distance along the slope is related to the x and y dimensions due to geometry. If the slope of the skiing surface is given to you, the angle of the phi is given to you. So in this way, you could try to substitute the equations and solve the problems gradually. For example, here you are replacing the time by x, replacing the time. Let's see. D sine phi is equal to 1/2 gt squared. T here comes from the equation number 3. So you could sort out the value of D by putting in the value of phi, 35 degrees. So these would follow naturally. You see, by putting this term from equation 3, and then this would be solved by making D as the subject of the formula. And then you put in the numbers to solve the equation. Vx is just 25 meters per second. And then you will find out what is xf and yf. Xf is d cosine theta from the geometry, and yf is minus d sine theta. It is falling downward, so that is why you have the minus sign at here. Okay, is there any problems apart from those raised in the chat? Well, for the time being, we finished the discussion on the projectile motion. Now let's try to work on some questions that is related to projectile motion. So at here, we would have a short quiz. Let's see if it works. Okay, log in again. Okay. Now we would be working on this. So please join in with the session number on the top left-hand corner. There are two questions only. There are two questions only. So, and the two questions are actually related to one another. So I will give you around, well, not more than 10 minutes to solve the problems. And it is, meanwhile, if you have any questions, you can ask me. Session number is on the left. If you cannot scan the QR code, you may just type in the URL. And you have to use your serial ID. You have to sign in with your net ID. Okay, we wait for 3 more minutes. Yes, there's only 2 questions. it's okay. Take your time. In any case, the questions are quite easy. Don't worry. I just leave the question on until the end of the lesson. So, in the meanwhile, I would be going back to the lecture slides. Yeah, in a very quick way, we have talked about the kinematics, which is concerned with the description of the object's motion. Especially, we have been talking about the one and two dimensional kinematic equation problems, as well as the vectors. And these are the vectors for describing the physical properties that have both magnitude and direction as well, and they will be useful later. On the other hand, the kinematic equations, they are just for describing the motion of the objects. As I've said, it would not give you any understanding on why the object would move. So the idea in the next unit 5, is that we would be describing the behavior of the objects by understanding how the objects move under different circumstances. And that is the idea of the Newton's law of motion. So once again, that is something very fundamental in the linear mechanics, and we would be just going back in the concepts in a very brief way. And many of the important problems in the linear mechanics comes from, for example, the Newton's second law, which, of course, you remember the equation. So that is F equals to ma. But apart from that, there is one apparently new topic which many of the classmates have mentioned and would like some more detailed explanation, and that is the concept of the coefficient of friction. So I will explain it in more details later. And here it is just a one-page summary on the Newton's laws, at least in terms of the important statements. The exact interpretation of these statements, I would really urge you to go to the textbook, because that will give you much more understanding on the topic. But the importance of these laws of motion, as I said, is that we are trying to jump out from simply knowing how the objects move into the important fact of why the objects move. Once we know why they move, we could start to control them. So first, we take a look at the three laws as a statement. The first law states that, well, this is a very, the laws in physics are usually very condensed language. So basically, every single word would have their exact meanings, kind of like the law books. kind of like the regulations in the world. So here, in the first law, it states that in the absence of external forces, an object at rest would remain at rest, and an object in motion would continue to be in motion with a constant velocity. So in this first law statement, it states that the object would remain its state. Either it is at rest or in constant velocity motion, unless it is under an external force. We will explain in the next slide. And then the second law would be that the familiar equation F equals to ma. It is the equation which connects the motion of an object to the external force, how it behaves under the presence of the external force. So it tells you F equals to ma. And thirdly, it is another scenario which is very important, and that is the action and reaction. When you have an action force from one body, it would receive a reaction that is equal in size but opposite in magnitude that acts back towards it. From the third law, actually it comes to the concept of a linear momentum, as we will see later in the lecture slides. So, first law first. According to the Newton's first law, it clearly states that in order to change the motion, what we need is a force. And it is not simply some forces that would change the motion. Actually, to be more precise, what we need is net force. We need to have a net force for the motion to take place. If the forces cancel one another, for example, if you have two forces putting head on, then you can expect that the two forces will cancel according to the vector addition, and there would be no force. So external force by itself is not sufficient. It is external net force that is required. But importantly, the first law states that you need to have this net force to change the motion. Otherwise, it would remain the same. Either it keeps on staying in place or it would move with constant velocity. This is in great contrast to what the people have been believing for more than 2,000 years, starting from ancient Greece. In ancient Greece, they saw the objects would eventually stop moving. So they believed that in order to keep objects moving, you need to provide some external force. But Newton says no. Actually, we need to provide a net force. Otherwise, it would keep on moving with constant velocity. And forces, they are vectors, and they could be added to one another by vector addition. So whenever you have multiple forces, you could add them, but when you do so, you need to use vectors. Okay, so these are something you expected to know already. So here you have the force which can be resolved, on the other hand, into components perpendicular to one another, which is a very useful trick whenever you are solving problems in the mechanics. And then with the Newton's first law comes the second law, and the statement in a mathematical form is simple and sometimes mentioned in too simple a way. The force is causing the change of the motion of the object by giving it an acceleration. And therefore, it is this force, in fact, not just one force, but the net force. It is the sum of forces. As you can see, this one, this symbol here, this symbol here correspond to the sum of different forces. Of course, they are vectors, so you need to have vector sum of the forces. That would give you a net force, and this net force would be responsible for the acceleration of the object along the direction of this net force. So the force, as you can see, is proportional to acceleration. Mass at here is just a proportional constant. This mass is a scalar. This acceleration and the net force, they are vectors. The two have the same direction. Mass have no direction. So the mass is just a proportional constant, but on the other hand, the mass is an important property of the object, which, according to the Newton's second law, it would represent what we call the inertia of the object, meaning that how reluctant the object would be towards motion when it is under an external force. So when you have an external force, if it is a net force, a constant one, you apply it to different objects. If the object would have a larger mass, it is more reluctant to accelerate. So this is a measurement on the property called inertia. So every object would have an inertia. And the mass is the measurement of the inertia. And we could determine the mass basically according to the acceleration generated by the same external force. So if the force are the same, then m1 over m2 is equal to a1 over a2. So that is how we can determine the mass of the object by comparing the acceleration generated through the same force. That is the idea. And the mass is, of course, a very important physical property. And at the same time, it is also related to a very similar physical property that is called weight. Now, mass is a measurement on the inertia, how reluctant it is towards acceleration, how reluctant it is towards acceleration when it is subjected to a net force. On the other hand, weight is a force. Weight is a force generated on an object due to the gravitational pull. So weight is equal to the magnitude. It is equal to the magnitude of the gravitational force exerted on the object. And according to the Newton's second law, this weight, which is the gravitational force acting on the object, is equal to m times g. G is the acceleration due to gravity. From now onwards, please take g as equal to 9.8. In the high school, you used to take it as 10, which is quite rough. So a more precise value is 9.8 or 9.81 meter per square second. And mass is a measurement of inertia, and it has a unit, SI unit of kg. Weight is a force acting on an object due to gravitational pull, so it would have a unit of Newton because it is a force. Mass does not change when you move from one place to another. I'm talking about the place being the place in space. So if you are on the Earth or on the Moon, you have the same mass. On the other hand, due to different gravitational pull, we have different values of weight. So that is the difference between the mass and the weight. And once again, okay, let me take some questions here. The inertia, oh, right. The idea of the inertia, once again, is just how resistant the object is towards the change of the state of motion when it is subjected to an external force. So it helps you to decide, but whenever an object is subjected to the external force, it would start to change its motion, be it initially at rest or be it initially at a constant velocity motion. So whenever you have a net force, the motion will change. And this inertia tells you how likely it is to change the motion by the same amount of external force. The larger the inertia, or that means the larger the mass, the more difficult it is to change the motion. That means the more difficult to accelerate the object. The magnitude of the acceleration is inversely proportional to the mass. So for the same external force, for the same net force, it would be equal to m1 times a1 or m2 times a2. So that is why the acceleration, the magnitude of acceleration on an object is inversely proportional to the mass. I'm not sure if that is something that you want, but hopefully you try to understand the inertia as the reluctance towards any change. But the English of the inertia is basically referring to the reluctance to have any change in the original property. Well, at here we are simply understanding the inertia as a physical property. So this is enough for us to understand why we have this concept of inertia. Later, actually, when we are going into another type of motion, the rotational motion, we would have yet another kind of inertia. Here, the object resists to change its linear motion when it is under an external force. When you are having an object, for example, a wheel, you can set it into rotation about its axis, but it may be hard or it may be easy, depending on its inertia. In that situation, the inertia depends on something else. But here, the inertia depends, or the linear motion, it depends on the mass. So the mass is an intrinsic property of the object, okay? So this is the Newton's second law. And for, I will probably answer it a little bit later for the difference between the mass and inertia. I probably should finish this slide first. So for the Newton's second law, we are not confining ourselves into one-dimensional problems. We could always encounter problems in the 3 dimensions. The technique of solving the problem is the same. We try to separate them into different components. And we could then consider to use the Newton's laws in different directions. So this is the way we tackle the problem of mechanics when it is under an external force. And remember, here, ma is by itself not a force, but it is actually the consequence of the object's motion due to the presence of an external force. So which is the cause and which is the effect, we have to be careful. The cause of the motion change is the external force, and the consequence is a change in the motion, which is proportional to the mass. So the mass is a measurement of the inertia, basically. The mass is the measurement of the inertia, basically. Inertia is just a concept, and the mass is the physical property that measures the inertia in the linear motion. That is how I would put it in the case of the linear mechanics. Okay. So in this sense, I would finish the lesson at here.